In vector calculus, the curl is a vector operator that describes the infinitesimal rotation of a three-dimensional vector field. At every point in the field, the curl of that point is represented by a vector. The attributes of this vector characterize the rotation at that point. The direction of the curl is the axis of rotation, as determined by the right-hand rule, and the magnitude of the curl is the magnitude of rotation. If the vector field represents the flow velocity of a moving fluid, then the curl is the circulation density of the fluid. A vector field whose curl is zero is called a rotational. The curl is a form of differentiation for vector fields. The corresponding form of the fundamental theorem of calculus is Stokes' theorem, which relates the surface integral of the curl of a vector field to the line integral of the vector field around the boundary curve. The alternative terminology rotor or rotational and alternative notations rot f and times f are often used for curl and curl f. Unlike the gradient and divergence, curl does not generalize simply to other dimensions. Some generalizations are possible, but only in 3 dimensions is the geometrically defined curl of a vector field again a vector field. This is a similar phenomenon as in the 3-dimensional cross product, and the connection is reflected in the notation times for the curl. The name curl was first suggested by James Clerk Maxwell in 1871, but the concept was apparently first used in the construction of an optical field theory by James McCulloch in 1839. Definition: the curl of a vector field f, denoted by curl f, or times f, or rot f, at a point is defined in terms of its projection onto various lines through the point. If is any unit vector, the projection of the curl of f onto is defined to be the limiting value of a closed line integral in a plane orthogonal to as the path used in the integral becomes infinitesimally close to the point, divided by the area enclosed. As such, the curl operator maps continuously differentiable functions f, R3 to continuous functions g, R3. In fact, it maps ck functions in R3 to ck1 functions in R3. Implicitly, curl is defined by where is a line integral along the boundary of the area in question, and a is the magnitude of the area. If is an outward pointing in plane normal, whereas is the unit vector perpendicular to the plane. Then the orientation of C is chosen so that a tangent vector to C is positively oriented if and only if forms a positively oriented basis for R3. The above formula means that the curl of a vector field is defined as the infinitesimal area density of the circulation of that field. To this definition fit naturally the Kelvin-Stokes theorem, as a global formula corresponding to the definition, and the following, easy to memorize, definition of the curl in curvilinear orthogonal coordinates, e.g., in Cartesian coordinates, spherical, cylindrical, or even elliptical or parabolical coordinates. Note that the equation for each component can be obtained by exchanging each occurrence of a subscript 1, 2, 3 in cyclic permutation, 1, 2, 2, 3, and 3, 1. If for the Cartesian coordinates and the orthogonal coordinates, then is the length of the coordinate vector corresponding to RUE. The remaining 2 components of curl result from cyclic permutation of indices 3, 1, 2, 1, 2, 3, 2, 3, 1. If the ball has a rough surface, the fluid flowing past it will make it rotate. The rotation axis points in the direction of the curl of the field at the center of the ball, and the angular speed of the rotation is half the magnitude of the curl at this point. Usage. In practice, the above definition is rarely used because in virtually all cases, the curl operator can be applied using some set of curvilinear coordinates, for which simpler representations have been derived. The notation times f has its origins in the similarities to the three-dimensional cross product, and it is useful as a mnemonic in Cartesian coordinates if is taken as a vector differential operator del. Such notation involving operators is common in physics and algebra. However, in certain coordinate systems, such as polar toroidal coordinates, using the notation times f will yield an incorrect result. Expanded in Cartesian coordinates, times f is for f composed of fx, fy, fz, where I, j, and k are the unit vectors for the x, y, and z axes, respectively. This expands as follows. Although expressed in terms of coordinates, the result is invariant under proper rotations of the coordinate axes, but the result inverts under reflection. In a general coordinate system, the curl is given by where epsilon denotes the Levi-Civita tensor and the covariant derivative. The metric tensor is used to lower the index on f, and the Einstein summation convention implies that repeated indices are summed over. Equivalently, where ek are the coordinate vector fields. Equivalently, using the exterior derivative, the curl can be expressed as herein are the musical isomorphisms, and as the Hodge dual. This formula shows how to calculate the curl of f in any coordinate system, and how to extend the curl to any oriented three-dimensional Riemannian manifold. Since this depends on a choice of orientation, curl is a chiral operation. In other words, if the orientation is reversed, then the direction of the curl is also reversed. Examples: a simple vector field. Take the vector field, which depends on x and y linearly. Its plot looks like this. Simply by visual inspection, we can see that the field is rotating. If we place a paddle wheel anywhere, we see immediately its tendency to rotate clockwise. Using the right-hand rule, we expect the curl to be into the page. If we are to keep a right-handed coordinate system, into the page will be in the negative z direction. The lack of x and y directions is analogous to the cross-product operation. If we calculate the curl, which is indeed in the negative z direction, as expected, in this case, the curl is actually a constant, irrespective of position. The amount of rotation in the above vector field is the same at any point. Plotting the curl of f is not very interesting. A more involved example: suppose we now consider a slightly more complicated vector field. Its plot. We might not see any rotation initially, but if we closely look at the right, we see a larger field at, say, x equals 4 than at x equals 3. Intuitively, if we placed a small paddle wheel there, the larger current on its right side would cause the paddle wheel to rotate clockwise, which corresponds to a curl in the negative z direction. By contrast, if we look at a point on the left and placed a small paddle wheel there, let's check out our guess by doing the math. Indeed, the curl is in the positive z direction for negative x and in the negative z direction for positive x, as expected. Since this curl is not the same at every point, its plot is a bit more interesting. We note that the plot of this curl has no dependence on y or z and is in the negative z direction for positive x and in the positive z direction for negative x. Identities in general curvilinear coordinates. The curl of a cross product of vector fields v and f can be shown to be interchanging the vector field v and operator. We arrive at the cross product of a vector field with curl of a vector field, using the Feynman subscript notation, f, which operates only on the vector field f. Another example is the curl of a vector field. It can be shown that in general coordinates, and this identity defines the vector Laplacian of f, symbolized as 2f. The curl of the gradient of any scalar field phi is always the zero vector field, which follows from the anti-symmetry in the definition of the curl, and the symmetry of second derivatives. If phi is a scalar-valued function and f is a vector field, then descriptive examples in a vector field describing the linear velocities of each part of a rotating disk. The curl has the same value at all points. Of the four Maxwell's equations, 2, Faraday's law and Ampere's law, can be compactly expressed using curl. Faraday's law states that the curl of an electric field is equal to the opposite of the time rate of change of the magnetic field, while Ampere's law relates the curl of the magnetic field to the current and rate of change of the electric field. Generalizations. The vector calculus operations of grad, curl, and div are most easily generalized and understood in the context of differential forms, which involves a number of steps. In a nutshell, they correspond to the derivatives of 0 forms, 1 forms, and 2 forms, respectively. The geometric interpretation of curl as rotation corresponds to identifying bivectors in 3 dimensions with the special orthogonal Lie algebra SO of infinitesimal rotations, while representing rotations by vectors corresponds to identifying 1 vectors and so, these all being 3-dimensional spaces. Differential forms in 3 dimensions. A differential 0 form is simply a function f. A differential 1 form is the following expression. A differential 2 form is the formal sum. And a differential 3 form is defined by a single term. The exterior derivative of a k-form in R3 is defined as the form from above, and on an oriented vector space with a non-degenerate form. There is an isomorphism between k-vectors and vectors, in particular on an oriented pseudo-Riemannian manifold. Thus on an oriented pseudo-Riemannian manifold, one can interchange k-forms, k-vector fields, forms, and vector fields. This is known as Hodge duality. Concretely, on R3 this is given by 1 forms and 1 vector fields. The 1 form corresponds to the vector field, 1 forms and 2 forms. 1 replaces dx by the dual quantity, and likewise, taking care of orientation, dy corresponds to and dz corresponds to, thus the form corresponds to the dual form. Thus, identifying 0 forms and 3 forms with functions, and 1 forms and 2 forms with vector fields. Grad takes a function to a vector field. Curl takes a vector field to a vector field. Div takes a vector field to a function. On the other hand, the fact that d2 equals 0 corresponds to the identities curl grad f equals 0, and for any function f or vector field grad and div generalize to all oriented pseudo-Riemannian manifolds with the same geometric interpretation. Because the spaces of 0 forms and n forms is always one-dimensional and can be identified with scalar functions, while the spaces of 1 forms and forms are always fiber-wise n-dimensional and can be identified with vector fields. Curl does not generalize in this way to 4 or more dimensions. In 4 dimensions the dimensions are 0, 1, 4, 6, 4, 1, 0, so the curl of a 1 vector field is a 2 vector field, which is fiber-wise 6-dimensional. 1 has which yields a sum of 6 independent terms, and cannot be identified with a 1 vector field. Nor can one meaningfully go from a 1 vector field to a 2 vector field to a 3 vector field, as taking the differential twice yields 0. Thus there is no call function from vector fields to vector fields in other dimensions arising in this way. However, one can define a curl of a vector field as a 2 vector field in general, as described below. Curl geometrically 2 vectors correspond to the exterior power lambda 2v, in the presence of an inner product. In coordinates these are the skew-symmetric matrices, which are geometrically considered as the special orthogonal Lie algebra SO of infinitesimal rotations. This has dimensions, and allows one to interpret the differential of a 1 vector field as its infinitesimal rotations. Only in 3 dimensions which is the most elegant and common case. In 2 dimensions the curl of a vector field is not a vector field but a function. As 2-dimensional rotations are given by an angle, note that this is not the div, but is rather perpendicular to it. In 3 dimensions the curl of a vector field is a vector field as is familiar, while in 4 dimensions the curl of a vector field is, geometrically, at each point an element of the six-dimensional Lie algebra. So, note also that the curl of a three-dimensional vector field which only depends on two coordinates is simply a vertical vector field whose magnitude is the curl of the two-dimensional vector field, as in the examples on this page. Considering curl as a two-vector field has been used to generalize vector calculus and associated physics to higher dimensions.